In this video, I'll be covering a topic on air resistance in fluids. Now, air resistance isn't really used much in AP Physics, or it's not usually covered in any introductory physics course, but it is pretty important. It is a concept that we need to understand, and drag force is really important in the physics world. So, I will introduce to you, if you're just watching this video because you're curious on what air resistance looks like in a physics classroom, you're welcome to watch till the end. So let's say we have someone and he goes down, we drop him, and his force exerted downward would just be m times g. Now let's say we have some particles. This is just a free body diagram of someone falling. It's not really that serious. Now let's say we have some particles, and these particles that this person collides into, causes a force upward. So let's define that force as some function of v with respect to some velocity. Now, if you can see here, this looks really familiar. This is just a free body diagram in physics. We have something that's going downward at something accelerated by gravity, some mass accelerated by gravity, and there is some upward force caused by the air particles, fluid particles, etc. Now, let's go over what terminal velocity is. Now, the concept of terminal velocity is just some velocity that you will reach such that no additional change will be made to that velocity. So that only occurs or happens when your sum of forces equals 0. When your f of v, some force given by some respect to velocity, some drag force with respect to velocity, is equal to some mass accelerated downward. Now this only applies to 1D kinematics. In 2D kinematics, I don't feel like fathoming that kind of physics right now. I don't think it's like possible for a human to do it. I'm not too sure, but let's focus on 1D kinematics for now. Now, terminal velocity is f of v equals m times g, where your free body diagram of the two directions of the forces applied would be equal and opposite in magnitude. Now, let's define our f of v to be some certain function that we can actually look at. Let's call this kv. K times v terminal equals m times g. All I'm going out here is just showing you how to solve for terminal velocity, because terminal velocity would be very important in the realm of air resistance and fluids. Now, this is just the equation that we have for solving for terminal velocity. All I really did was divide k to both sides, and you would use this in physics. If you have physics problems that actually deal with a lot of air resistance, you can just assume if there's a situation where you are at a point where you reach terminal velocity, you can just replace it with mg over k. It helps with notation. It may clear up some Taylor expansion uncertainties. You never know. It may just simplify some things that can turn into a Taylor expansion series where you can eliminate more terms. And it could just be helpful in general. It's a helpful tool. So let's go ahead and look at the actual air resistance problem or fluid resistance problem. Let's say we have a rock with a mass that falls from a rest. So v equals 0 initially. So v naught equals 0. V at time equals 0 is 0. Falls through a viscous medium. The rock is acted on by a net constant downward force of 18 newtons. So what this means is that the rock exerts an 18 newton force downward constantly, and gives some description about the scenario. We don't really care about that. And by a fluid resistance force of f of v equals kv. So remember those particles I was talking about? They do exert some function of force. So that's actually given to us right here. F of v equals kv. Now, kV or your drag force doesn't always have to look like kV. It could look like kV squared. It could look like AND or whatever bunch of random letters times the velocity. There's a lot of many different forms that could be given, but let's just focus on this form for now, where V is the speed and K equals 2.2. So cool, we're actually given the K constant. Now, part A asks for initial acceleration, part B asks for a certain acceleration at when V equals 3, and part C asks for the terminal velocity. So we did review part C. We will go over that at the end of the problem again. Now let's go over part A. We do have a rock. We have some viscous fluid. It's going downward. So this rock exerts some force F of y. It said 18 newtons, but let's just keep it symbolic for now. Some F of y right here. And kV. The kV is just the drag force, so the particles are like the particles it's bumping into. It's like adding up to be some constant k that we know, and velocity. So how do we approach a problem where we have to solve for acceleration with forces? Like, how do we do that with air resistance too? Now, we would need to start off with the sum of forces. F equals ma. Newton's second law, F equals ma. Let's go ahead and write that down. So when F equals ma, we can look at the problem again to see what our sum of forces are. So let's go ahead and define downward as positive and upward as negative. And I do this because the trajectory of the rock is only going downward. It's not going to fly up. The fluid is not listed to fly it up. It will just go downward. So if it goes downward, and if it only goes downward, we should just consider the problem downward to be positive, because why work with more negative numbers? It will just make it more confusing. So let's identify the sum of forces. We have an F of y, and we have a kV going exactly opposite and upward. So let's go ahead and subtract those two and set that equal to ma. Now, I rewrote ma here to help us solve for our problem. This is a very important step. So writing A as dV over dt is actually going to be the main component of this differential equation that would help us solve for the problem. Now, a lot of you haven't learned differential equations yet. It's pretty easy. I'll go over it in this video. This is an easy example of differential equations. There are harder ones. There are way harder ones. But we know that A is also dV over dt, because any change associated in velocity is due to acceleration. So dV over dt is just derivative. It's just calculus, pre-calculus, whatever you consider. Now, I will divide every side by negative k just to make our problem cleaner. So let's go ahead and do that. Every side is divided by negative k. And I will go ahead and also rearrange the problem because I just want to make it easier. So let's go ahead and rearrange it. It's just the same exact symbolic equation. It's just differently. It just looks different because I rearranged it and simplified it to make it look better. I do suggest dividing it by negative k. That does make the problem easier, and I will show you why. So we need to construct this into a differential equation problem. Now, the math majors will hate me for this, but I will multiply dt to both sides. Now, why do math majors hate this? Well, dt is oftentimes considered a very infinitely small portion, such that something approaches zero, or in this case, time approaches zero. And essentially, you're just multiplying zero on both sides, and that is just not correct in any way, just to call an equation equal. But if you want to do it properly, you would have to deal with delta t, delta v. It's just arbitrary stuff that will come later in maths, in whatever math that you guys take to choose, or take this, take that. Doesn't really matter. For this, I would just keep multiplying dt on both sides. Whatever, you can hate me all you want. I will maybe post another video covering this, maybe not. But yeah, let's just keep it that way. Let's go ahead and just multiply this portion over here to that side, or more specifically, cancel this part out and move it to that side. Divide this term over here to that side. Because I have a dv on this side, I have a v over here. So when I do integrate it, I want this v to be on this side so that it's integratable. So let's go ahead and just replace the terms. Just swap. There's a lot of swapping. Just simple algebra. Not too much to it. And let's go ahead and integrate. So when you integrate, pay attention to this equation. You will have a t naught. Sometime you start from the beginning that ends at some arbitrary time. I want to integrate across this portion of the equation so that it will give me what I want. In this case, it would be some certain time that I want, the time in between these two arbitrary times. Now, over here is velocity. We have some velocity that starts at the beginning and some velocity that starts at the end of the velocity, or some velocity at the end of time. Now, if your question asks or says that it starts at 1 second and ends at 3 seconds, then those would be your bounds for your time. And these would apply here too. The arbitrary t's have to be the same. This v of t, some arbitrary velocity at some certain time, has to be the same time, your arbitrary time that you set. That's why it's just t. I didn't notate it differently, it's just the correct way. Now, let's go ahead and integrate with respect to each variable. T naught is just simply 0 because in this question, time starts at 0 seconds. So our left side can be just simply the term that over here. We just attach a t here. There's no plus c because these are definite integrals. And if we look at the right side, we do have a simplified natural log equation. It's just algebra. I won't be going over too much algebra here because these should be taught in like 10th grade or even earlier. But there should be videos explaining on how to rewrite your algebra. And yeah, let's go ahead and e both sides. I don't like this natural log. I do want to solve for this v of t because when I solve for this v of t, what I would get is some velocity function with respect to time. That I can use to find acceleration, I can use to find position, I can use to find everything. So let's go ahead and solve for the v of t. Let's just e both sides. Let's just multiply both sides by negative f of y over k. So from here on out, it's just simple algebra. V at t equals 0 is just 0 because velocity starts at 0, as stated in the problem. If your velocity starts with something, then you cannot have the luxury of just simply multiplying this one term over here. You will have to multiply these. Now, we just have to multiply negative f of y over k on both sides. We just have to add negative f of y over k on both sides because over here we have a term over here. So let's just go ahead and do that. And now we have our function of velocity with respect to time. Now let's go ahead and use this and solve for a naught, or the acceleration momentarily, or at the moment it begins being dropped. So t equals 0. So we know at a naught is when t equals 0. Now, how do we get acceleration just from this? Well, it's just simple calculus. We just derive this. We take the derivative of this because the derivative of velocity function is just acceleration with respect to time. So let's go ahead and do that. All I really did here was just some exponent rule. Where if you remember how to take derivatives of the e function, you just, this whole thing, same thing, multiplied by the term in front of the t over here. And then obviously this constant goes away because the only variable over here is t. All we have to do is just sub in t equals 0, and sub in our other answers as well, because we're given that f of y is 18 newtons, 3 is mass, or the mass of the rock is 3, and e of 0, t equals 0, so e of 0 is correct. And 18 divided by 3 is just 6. Now, this is actually really simple beyond the math that we just did. The next problem just asks us to find what is the speed, or what is the acceleration when the speed is 3 meters per second. Well, all you have to do here is actually find the time that the velocity reaches 3 meters per second. and you would use that same time and plug it into the acceleration function. So you would get your acceleration at that time as well, because the acceleration at that time resonates with the velocity at 3 meters per second. That's how you connect the two equations. Now, let's go ahead and do that. Let's just sub in some arbitrary time, or velocity at some arbitrary time would be assumed to be 3. So let's go ahead and just put a 3 there. I just replaced this front part with 3. That's all I really did. And from here on out, we just need to solve for the time that it took for the velocity to reach 3 meters per second. It's just algebra once again. We subtract the constant. We subtract this constant to both sides. We multiply the reciprocal of this constant to both sides. And we natural log both sides, and we multiply this to get this out. So let's go ahead and do that. Subtract that to both sides and multiply this portion over here, or the reciprocal. I actually went ahead and distributed the negative k over f of y just to make our problem look a lot easier, because now you have a 1 minus 3k over f of y, and I have e of this. Take the natural log, and once you take the natural log, you will have no e over here, so you just have negative k over mt, and you just multiply the reciprocal once again, and you solve for your t. So now we have some time that the velocity equals 3 meters per second. Let's go ahead and plug in our numbers and find this time. So we get 0.628 seconds. This will be the time that it takes for the velocity to reach 3 meters per second. Now, let's use this time to find the acceleration, because our acceleration equation has some t that we can sub in for. Let's bring the acceleration equation back, and let's go ahead and just sub in all the terms. We have our t that's now known, and we have everything that's also known. So once we just do the substitution, it would just be 3.8 meters per second squared. So all in all, it's not too hard. Once you get the velocity function, you can basically go anywhere. Like if it asks for position at some certain time, you solve for that. Asks for acceleration at a certain time, solve for that. Velocity at some certain time, solve for that. Yada yada yada. The last question is find the terminal speed. We actually went over this. It's actually the easiest part of the question. Let's bring up the force diagram once again. Like I discussed earlier, the only time you'd have terminal velocity is when your net force equals 0. So what that means is this bottom portion has to minus this top portion has to equal 0. Also means that these have to be equal in magnitude. So let's go ahead and write that out. F of y equals k of v, or k times v, or in this case v terminal. It has to be v terminal. So let's go ahead and just sub in the numbers, and we get 8.18 meters per second. So these are actually really easy problems. None of these are hard at all. It does take a little math at the beginning, but all in all, it's actually really simple.